Hello, and welcome to my talk about sea monsters in the Age of Dinosaurs. I am Danielle-Serratos, Director-Curator at the Fundy Geological Museum in Parsboro, Nova Scotia, and today I will tell you about the major groups of marine reptiles that lived millions of years ago, as well as one species of marine reptile that I described and published with my colleagues, Drs. Druckenmiller and Benson, back in 2016. So let's get started. Let's break down that title a bit. The Age of Dinosaurs, aka the Mesozoic era, outlined in the red rectangle, lasted 186 million years, from 252 million years to 66 million years ago. Our species, Homo sapien, has been around approximately 0.1% of the time that dinosaurs ruled the world, and you can see our human blip in the red arrow. Now, for sea monsters, why don't I just call them dinosaurs? Well, because they're not. We're going to briefly discuss all of these groups listed here today, but I think that it's interesting to note that the only group we are unclear about its evolutionary relationships are modern turtles and how they relate to the other marine reptile groups. Are they a sister group to the extinct groups of traditional marine reptiles in red and the true reptiles and archosaurs in black? Or are turtles an ancestor group to those clades within reptilia? Well, paleontologists will figure it out one day. To start off with, we're going to discuss the Triassic period. There were four major groups of Triassic marine reptiles. In the top, outlined in the yellow rectangle, you'll see the Sauropterygians. Those are nothosaurs, placodonts, and pachypleurosaurs. On the bottom left, you'll see ichthyosaurs, bottom middle, early turtles, and bottom right, the latosaurs. We're going to dive deep into, pun intended, the Sauropterygians first. So the nothosaurs on the bottom left are commonly compared to seals, as they would hunt their prey in the water, but would most likely come up on land to enjoy their meal. Placodonts in the middle are sort of half walrus, half turtle looking animals. These marine reptiles would have been negatively buoyant in the water, aka they sank, which would have been useful as they primarily fed on shelled invertebrates like mollusks on the seafloor. On the bottom right there, you'll see a pachypleurosaur. Skeletal analysis of this group has led researchers to think that pachypleurosaurs undulated their entire body, similar to how sea snakes get through the water. They eventually began to use their limbs to steer and then push themselves through the water, not unlike how humans swim today. This group has the highest likelihood of being ancestors to my favorite group of marine reptiles, which leads me to the Jurassic. So during the Jurassic period, the only Sauropterygians that were around were plesiosaurs. You'll see an early plesiosaur paleo reconstruction on the top left. There were also ichthyosaurs, turtles with partial hard shells, thalatosaurs, and thalatosaucians. So 5 major groups of marine reptiles during this Jurassic period. After the Triassic-Jurassic mass extinction and the breakup of the supercontinent Pangaea, a new marine reptile group diversified, the thalatosaucians. These marine reptiles were most likely mimicked modern sea turtles in laying their eggs on land and returning to the sea after. We refer to these fossils as crocodilomorphs because they look very similar to modern crocodiles, but they have enough differences in their anatomy to be considered a separate group of animals, You'll notice in these paleo reconstruction artistic images here, what we think their soft tissue looked like, and they most likely had webbed appendages instead of fingers. There's also some evidence that the tails on some of these fossils would have been propulsionary, which basically just means that they used the movement of their tail to push them through the water. Now for the Cretaceous period, arguably one of the more interesting, just because of how diverse some of these groups of marine reptiles expanded. During the Cretaceous, of course, turtles were around because, well, they were around before the Cretaceous and they're still around today. That's what we call extant, when they're still around today. They would have been more recognizable compared to modern turtles and having a hard shell, the plastron, and the carapace. Mosasaurs on the top right there, you might recognize this animal if you've seen Jurassic World. More on mosasaurs in a second. Ichthyosaurs on the bottom left. So a lot of people look at images of ichthyosaurs and say, well, it kind of looks like a dolphin. Or if you look at the tails, it kind of looks like a tuna. Ichthyosaurs are what we commonly consider to be the poster animals for convergent evolution. And this is the idea that you have two different groups of animals that have evolved completely separate from one another. They're not closely related at all, but they look very similar because they have evolved the same and anatomical characteristics that will benefit them in their environment and the prey that they hunt, or if they're herbivores or, not predators, however they're feeding. So ichthyosaurs kind of have this long, lean, hydrodynamic body shape similar to dolphins because when they were alive, they would have hunted down their prey very similar to dolphins do today. Both groups were piscivorous, which means they both ate fish. Plesiosaurs, on the bottom right there, come in a wide variety of body shapes and sizes. In fact, this group has maintained the largest diversity throughout the entire Mesozoic era. At the beginning of the Cretaceous period, the scariest group of Mesozoic marine reptiles showed up, aka the mosasaurs. Mosasaurs had dual rows of teeth in their upper jaw, and their jaw itself was double hinged, which just meant instead of having a scissor-like motion in how humans open and close their jaws, the mosasaurs could shift at two inflection points. So their jaws, when they closed, were more like a wrench and less like scissors. Mosasaur speeds in the water are estimated to be similar to modern sea lions, with the potential to get as fast as modern dolphins. These would have been apex predators hunting down their prey through speed. We call mosasaurs true reptiles because they're more closely related to modern lizards and snakes than they are their other Mesozoic marine reptile compatriots like ichthyosaurs and plesiosaurs. Now, this graph is not all that user-friendly, but it's an interesting one once you realize that it's talking about species diversification throughout the entirety of the Mesozoic. So you can see in the green that Sauropterygians, aka mostly plesiosaurs, had a very high number of individual species early on in the Triassic, and it decreased on and off until the mid-Cretaceous. And then it had a nice spike upwards and then a vast decrease at the end of the Cretaceous, but actually started to come back. I'll talk more about this when I talk about the genus and species that I described. The other thing that's worth noting here is plesiosaurs and Sauropterygians were not the only group that decreased rapidly towards the end of the Cretaceous period. In fact, ichthyosaurs in the dark blue went completely extinct before the end Cretaceous mass extinction event that wiped out, well, almost all the marine reptiles and most of the dinosaurs too. Getting back to my favorite group of marine reptiles, plesiosaurs. Plesiosaurs are broken into two major morphotypes or body types. So on the left, you'll see the plesiosauromorphs. These are large-headed, large-bodied plesiosaurs that have a neck, but it's not super noticeable where that starts and stops compared to the head and the body. On the right, you have plesiosauromorphs. Now, these animals could have been similar to Kyphakia that you see at the top of the right-hand column, where the head and neck are roughly the same length as the body and tail, or you can have the extremely elongate-necked plesiosaurs called elasmosaurs, like Albertanectes, which currently holds the entirety of history of the planet world record for longest neck, both in terms of length and in terms of the number of neck vertebrae. That number is currently at 76 neck vertebrae. Mammals have 7 for comparison. Even giraffes, actually. A lot of people think, well, the giraffe neck is so long, it must have a bunch more neck bones in it. But that's not true, actually. They still have the same number as humans and all other mammals. They're just elongated vertebrae. Now, elasmosaurs, or these long-necked plesiosaurs, used to be thought of as kind of floating at the top of the water with a swan neck appearance where they held their whole neck and head out of the water. If you're familiar with the Loch Ness Monster images and the hoax around that, this will be a familiar concept to you. In actuality, computer modeling in the 1960s up until today has consistently provided evidence that the muscles in a plesiosaur's neck would not have been strong enough to hold their head upright like that, let alone upright outside the water. So you'll see the bottom image is at the American Museum of Natural History in New York City, and this is the correct way to mount an elasmosaur skeleton. Now, at this point, I'm going to start narrowing in on talking about the genus and species that I described. You'll notice that this map shows the continents are a little bit different than what they look like in modern maps. That's because this is a paleo map at the end of the Cretaceous period, roughly 70 million years ago. Now, you'll notice there's a bit difference in the way North America in particular looks. It's got a lot more water than what we would associate with today. Well, that's because the Cretaceous was a much warmer global climate than it is today. In fact, it was so warm at the end of the Cretaceous that there was no sea ice, either in Antarctica or the Arctic. So, because sea levels were a lot higher due to there not being any sea ice, the middle of North America was an epicontinental sea. An epicontinental sea just means that you have a seaway over a continental plate, similar to how the Mediterranean Sea exists today. Well, because that seaway was there and in places was up to 500 meters deep, you have these nice large marine reptile fossils that you can find right smack dab in the middle of North America. This particular fossil was found by an elk hunter who was at the Charles M. Russell Wildlife Refuge. He was walking through a drainage ditch trying to, I guess, sneak up on elk. I'm not sure. And he stumbled on this big old block of what looked like concrete, and then he noticed the neck vertebrae. So he took a bunch of photos informed the park rangers there about the location. He took a GPS, which was fantastic. Unfortunately, between the time of discovery and the time park rangers and paleontologists got back to the site, there was a spring flash flood that wiped out all of the vertebrae that you can see at the bottom of the image there. So when Dr. Druckenmiller and his team got out to pull this fossil out of this drainage ditch, it was, for the most part, everything that you can see that looks like concrete, as well as every bone that was in that cliffside that's sort of out of the picture in the bottom right corner there. But since we have photos, we have a fairly good understanding of how many neck vertebrae this animal would have had when it was alive. Now, I've talked a bit about sort of 70 million years and knowing how old this, or how long ago this animal was alive from today. But how do we know that? Well, this particular genus and species of elasmosaur, plesiosaur, was dated using ammonite biostratigraphy. Since we didn't have any forams or diatoms in the matrix or the rock around the fossil, and absolute dating, where you have chemical radioactive isotope dating, was not available in this location because the fossil had been contaminated by barium. So ammonites, like the two on the right here, are such a diverse group of organisms. Their species are so clearly identifiable from one another, and they change very quickly, the species do, over geologic time, and they have a global distribution. So once we had a good understanding of how many different species of ammonites there were around the world, early paleontologists actually put together a geologic timescale using animals like this to determine how old something was in comparison to the other fossils. Well, eventually, absolute dating with radioactive isotopes was a thing, and those dates were compared to the relative dating methods used with biostratigraphy. And it turns out a lot of those numbers were really, really accurate. So we actually have two ways of dating fossils right now, and they complement each other really well when you have situations like this where you can only have one of the two methods available. Now, my job as a museum director and curator has research components, grant writing components, administrative field work, all kinds of interesting things. So I get to do a little bit of, well, not everything, but a lot of different things in my job. But when I was a grad student, most of my work in the lab was actually preparing the fossil and writing the paper describing it. So if you're interested in fossil prep, here are a couple of images that might give you a better idea of what that looks like in the lab. On the left, you have mechanical preparation. This is where we use a pneumatic device that is basically a pen-sized jackhammer where you chip away at rocks surrounding fossil bones. On the right, you have chemical preparation. So this plesiosaur that I worked on, we used a 7% formic acid bath. Essentially, you pick out the chunk of bone that you want to remove rock from, and you dunk it in an acid bath for, well, on and off for usually 8 to 12 hours at a time. And it usually takes a couple months to get down to where you've removed most of the rock. It's a slow process, but as you can see from the images, it leaves the bones very clean and intact if you do it properly. I was fortunate to learn how to illustrate my fossil for publication using Adobe Illustrator with the help of the laser scan that you see at the top of this image. We worked with the Idaho Virtualization Lab. They actually came out to Alaska where I was prepping this fossil and did this 3D scan of the skull for us for free, which was phenomenal. I really enjoyed the opportunity to work with this sort of advanced technology. And it taught me a lot about how we visualize scientific specimens as well as how to communicate that with the public. If this is ever something that you are interested in doing, I would highly encourage you to learn how to use Adobe Illustrator. This image that I brought up next is sort of the scientific outline of the entirety of the specimen that we pulled from the field. As you can see, we have the majority of the animal here, but the majority is not prepared. So we had head, part of the neck, flippers, tail, parts of the back vertebrae, what we call the coracoid, which is kind of a breastbone type structure in marine reptiles. There's a lot more that needs to be prepped out. Unfortunately, it takes many years, and well, if you're one person, it takes many years to prep out something this big. If you have a whole team, it would still take quite a long while. We were fortunate in prepping out this specimen. We did discover gastralia, which are similar to ribs, except they interlace at the bottom of the abdomen and basically provide some structure for the torso of the animal as it's swimming through the water. So that was really cool because we actually got to see how those bones fuse together as the animal becomes an adult. And we did find some stomach contents. So this animal had gastralia, which would be small pebbles and rocks that this animal would have ingested on purpose during its lifetime to sort of counteract the positive buoyancy that the animal would have been born with. Also, there's a good chance that those gastroliths or those rocks would have helped in digestion because plesiosaurs didn't have a knife and a fork to eat its fish with. And so those rocks probably would have helped break down a lot of those really small fish bones that they would have been ingesting. So overall, we had the majority of this animal preserved, and we published the description back in 2016. Interestingly enough, we were one of the first publications to have both the left and the right ilia bones, which I guess I should go back and show you. That would be on the left side of the screen. It says left IL, and then above that there's an IL. So these bones don't look all that important, but they're actually the bones that provide evidence that speaks to plesiosaurs not being able to beach themselves and walk around on land. They would have been only marine or estuarine organisms. We ended up naming the animal Nakonanectes bradti in honor of the indigenous groups in the area that the fossil came from and the elk hunter that discovered the fossil in the first place. This animal was geologically the most recent elasmosaur from the Western Interior Seaway. That's the body of water that was in the middle of North America during the Cretaceous period. And I talked a little bit earlier about how plesiosaurs were some of the most diverse groups of marine reptiles, especially in the Cretaceous. And it's interesting because I put the sort of body image of an Albertanectes on above Nakonanectes. So both of these plesiosaurs were swimming in the same sea within 5 million years of each other, so roughly around the same time. And they are two completely different evolutionary tracks of plesiosaurs in the same sea around the same geologic time. So it's clear to us now, or I shouldn't say it's clear, it's becoming more clear that elasmosaurs were evolving longer necks, bigger bodies, At the same time, they were reducing neck length and body size. Most likely this is driven by the ecological niches that they were fulfilling, the prey that they were hunting, and the fact that other marine reptiles in the Mesozoic were dying out or had previously died out, opening up the possibilities for plesiosaurs to be more successful. Well, I really appreciate your attention if you've made it to the end of this talk. If you have any questions about this, I am active on Facebook through the Fundy Geological Museum's webpage. I also have a Twitter account, and the museum has a Twitter account as well at Fundy Geo. I hope you enjoyed this talk, and maybe we'll meet again.